Welcome to this video concerning advanced calculus, and today we approach Green's theorem. Green's theorem is very important because is important in itself, but it is important to obtain other proofs. So that Green's theorem says, let's C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let S be a region bounded by C. If pi and q are two functions of x and y defined in the union of S and C, having continuous partial derivatives, then the integral of pi in the x plus q in the y is equal to the integral on S over the q over the x minus the pi over the y index the y. The positive orientation, I recall, that is a counterclockwise orientation as indicated by the arrow. So that we can imagine C, the contour C, as a polygon. For example, an hexagon, so that we can imagine to divide and pulverize this polygon in a multiplicity of possibly infinitesimal rectangle triangles. For example, as I've done in the draw, in this draw, any rectangle triangle is endowed by an arrow, so that we have any side of the triangle is endowed by a flux denoted by an arrow. We have an arrow that leads from this vertex to this vertex, an arrow that leads from this vertex to this vertex, finally, since it is a closed figure, we have an arrow that leads from this vertex to this vertex. So that we recall that this side is cathetus is sine of theta, the length of this cathetus is sine of theta, the length of this cathetus is cosine of theta, and hypotenuse. So that with this notation we can approach the circulation lemma that says that let A with 1, A with 2 be two congruent triangles whose sides take in uniformly oriented fluxes. Then the circulation on the union of A with 1 and A with 2 is a counter circulation. That is, the fluxes in the inner of the polygon is void. And how can we prove a circulation lemma? It's very simple, because if we take two rectangle triangles, with uniformly oriented fluxes, we have that between this vertex and this vertex there is a flux with orientation, with opposite orientation of with respect of the flux of the other triangle. So that imagine to join the two congruent triangles so that we can obtain a rectangle. And of course, as I've said, the inner circulation is void because the two fluxes cancel out, mutually cancel out. So that it remains a circulation on the rectangle with a flux between this vertex and this vertex, a flux between this vertex and this vertex, a flux between vertex and this vertex, and finally a flux between this vertex and this vertex. So that I think the proof should be clear. Now we have drawn an observation and most a principle. That agree with this proof. And is useful to complete the proof of Green's theorem. Let gamma be a closed broken line whose segments take in some positively oriented fluxes. We can cancel positively, whose segments take in some oriented fluxes. If capital S equal to S1 join S2 join Sn is the set of such segments, and capital S with 0, capital S with 1 is a subset of S, pi with 0, pi with 1 points on the broken like, such that S with 0 and S with 1 meet in pi with 0 and pi with 1. Then there are two independent and disjoint paths characterized by opposite orientations on the broken line, respectively on S, capital S with 0 and on capital S with 1, joining P, pi with 0 to pi with 1. This is almost clear because if we consider a triangle, we can immediately see that joining this arrow with this arrow, we construct a path by this vertex, from this vertex to this vertex. But if we consider an arrow from this vertex to this vertex, we have two disjoint paths. Now we can call pi with 0 this vertex, pi with 1 this vertex, and we can write the set as capital S with 0 is the set containing sin theta and cosine theta. And finally, the singleton at capital S with 1 as the singleton given from this vector. The vector V, so that this principle is now clear. There's a path that connects pi with 0 to pi with 1 passing by this vertex, and the second path that connects pi with 0 to pi with 1 passing through the hypotenages. The path V. Now we have the tools to complete the proof. We can set firstly with to write the right hand side as the double integral of f of the cube over the x minus the pi over the y in the x the y. Now setting delta, recall that we have pulverized the polygon in a multitude of possibly infinitesimal rectangle triangles, so that delta n plus 1 is equal to sine theta, where theta is an angle that we can theta with n plus 1 is an angle that we over whose nature which is shown precise So that if we set theta n plus 1 as this difference, the derivative theta theta n plus 1 dash is cosine theta n plus 1 minus cosine theta n. Now we have to precise the nature of the angle theta. The angle theta is the angle of the possibly infinitesimal rectangle triangles in which we have polarized the polygon. This is cosine theta and this is sin theta. So that since the area of the triangles is possibly infinitesimal, we can transform the integrals, the double integrals in a double sum. A double sum of Q cosine theta n plus 1 sin theta n plus 1 minus Q of cosine theta n sin theta n over theta dash so that we minus pi cosine theta n plus 1 sin theta n plus 1 pi cosine theta n sin theta n. over delta n plus 1 multiplied delta dash n plus 1 delta n plus 1. But now it's possible to simplify this product. Delta n plus 1 cancel delta n plus 1 at the denominator, and delta dash n plus 1 cancel delta dash n plus 1 at the denominator here. So that given this simplification, we have again a double sum on m, and on m. Calling this difference delta n plus 1 with delta n plus 1 cube for delta n plus 1 plus here is a minus. Minus for minus is plus. Delta n plus 1 pi for delta dash n plus 1. But since any triangle is possibly infinitesimal, this double sum becomes an integral by circulation lemma, and becomes pi z plus q y. So that we have finished, because with the equivalence of this double integral and this circuit integral, circulation integral, talk, and I say that the next video will be devoted to Stokes' theorem.